Thank you, Dan. Those of you who know me probably associate me still with Damian Electric, or even if you go back further with Kotecki. But I retired in 2007, so I've been out on the circuit. And a year ago, I relocated from the Cleveland area to Chapel Hill, North Carolina, so that shoveling snow is no longer in my job description. Could we kill the lights in the front row? I think it makes those lights more visible. Thank you. Okay, so in logical order, this would have probably been the first presentation of the day, but it wasn't for reasons best on the gun. Anyway, where I'd like to start is, why on earth do duplex stainless steels exist in the first place? Well, the answer is chloride stress corrosion cracking. We talked about all kinds of corrosion tests this morning, and it was always pitting. The real reason they exist isn't pitting. It's chloride stress corrosion cracking. The problem is that the austenitic stainless steels like 304L and 316L are highly susceptible to chloride stress corrosion cracking. The ferritic stainless steels are highly resistant to chloride stress corrosion. The ferritic stainless steels, however, are really ugly critters to weld. The reason is grain. The toughness vanishes when you weld on them because of grain. Duplex stainless steels, then, come into the picture as a way to combine the properties of the austenitic stainless and the properties of duplex stainless. Now, you guys all know Murphy's Law, right? Anything can go wrong, will go wrong. And if you apply Murphy's Law to alloy design, what would Murphy's Law tell you about this situation? It would tell you that if you combine two alloy systems, you will get the worst features of both. But that's not what happens with duplex. Duplex stainless steel is a clear violation of Murphy's Law. So, anyway, in order to get chloride stress corrosion cracking, you need chlorides, you need tensile stress. Tensile stress is automatic with welds. So you can always anticipate yield point residual stresses around a weld. Better. So you're always going to be susceptible to chloride stress corrosion cracking in the alloys like 304, 316. That's why duplexes are interesting. This is a picture of chloride stress corrosion crack, or a whole lot of chloride stress corrosion cracks. This is in 304 stainless, 304L. On the left side, you see the unetched appearance, and the signature of chloride stress corrosion cracking is cracked branching. So you have a crack at the surface that becomes a multitude of cracked subsurface. And on the right-hand side, you have the same picture, but it's in this area here, and it's enlarged, and the samples have been etched. And the reason for the etching is to show you that the chloride stress corrosion crack doesn't care about grain boundaries. You can see here, you have grain boundaries, and you have a crack going right through a grain. It jumps from grain to grain to grain. It doesn't care about grain boundaries. This has nothing to do with sensitization. It has everything to do with chlorides and chloride stress corrosion cracking. Now you got two ways to cure chloride stress corrosion cracking in stainless steel. One way is lots of ferrite. That originally led people into all kinds of advancements in what I call third generation ferritic stainless steels. These are the ferritic stainless steels like type 444, 18 chrome, 2 moly, very low carbon, very low nitrogen. Or 26-1 is another alloy, 26 chrome, 1 moly, and very low nitrogen, very low carbon. They're ugly to fabricate in any kind of thickness beyond sheet metal, so we try not to do that. The other alternative was to go with lots of nickel, get away from compositions that were susceptible. And that takes you into nickel-based alloys or the so-called superaustenitic stainless steel. 25 nickel, 20 chrome kind of alloys or something like that. Duplex turns out to be the cheapest alternative and the most friendly because you get those fabrication properties that are like austenitic stainless steels. In particular, grain growth doesn't hurt as it does with fluidic stainless steels. Okay, so in a duplex stainless steel, you got approximately equal amounts of ferrite and austenite. Some say 50%, 50-50 or something like that. These things give you resistance to chloride stress corrosion cracking like the ferritic stainless steels. They give you fabrication properties that are more like austenitic stainless steels, and they give you a bonus, a doubling of the yield strength. That was already mentioned before. Now, how do duplex stainless steels come about? What you see here is a section through a ternary iron chromium nickel diagram at a constant iron level. Okay, so it's 70% iron. And what you're doing as you go from left to right across this diagram is you're going from no nickel up to 20% nickel and from 30% chrome down to 10% chrome. And then up at the top here we have liquid, and in the center here we have this triangle. Kotecki triangle, that's called. That's where liquid plus ferrite plus austenite coexist. It's a very small range where they coexist, all three phases at once. But the important thing about it is that an ordinary austenitic stainless steel, like 304L for example, is going to have a composition very close to the edge of this triangle, so that the metal is going to solidify as liquid going to liquid plus ferrite, going to liquid plus ferrite plus austenite, then into ferrite plus austenite, and eventually down to 100% austenite. That's why your 304 base metal doesn't contain any ferrite. However, if you take that 304 base metal and you melt it with a gas tungsten arc torch, no filament, just melt, and then measure the ferrite, you will find there's some ferrite. And that's because during solidification, you get some formation of ferrite, and some of that ferrite survives to room temperature. To get rid of it, you need to cause chromium to diffuse out of the ferrite and nickel to diffuse into the ferrite. Ferrite and the austenite have different chemical compositions. All right, now a duplex stainless steel starts out further to the left in the diagram, someplace over here, where its solidification goes from liquid to ferrite, the liquid plus ferrite, to 100% ferrite. And 100% ferrite exists for an appreciable temperature range. And then as you cool further, it enters into the two-phase field where ferrite and austenite coexist. And that ferrite plus austenite will coexist until the cooling has gone so far that nothing else happens. And that's what you freeze in at room temperature. Now, how easily the austenite forms depends upon how high the temperature is with the first austenite. If the first austenite forms at a high temperature, then diffusion is pretty rapid. Chromium can partition to the ferrite, nickel can partition to the austenite, and it's not very dependent upon cooling. But if the first austenite doesn't show up until a rather low temperature, now the diffusion of chromium and nickel is very limited. The end result is that you don't partition chromium and nickel. And that's where you can get into some trouble with these things, because you're locking in very high ferrite. You don't get anywhere near equilibrium transformation of austenite, and the end result is you get very poor mechanical properties. Okay. That leads us to starting to talk about the duplex stainless steels in terms of generations. People talk about duplex stainless steel today as if this is really new technology. But duplex stainless steels are older than I am. Those things existed already in the 1930s. You see these two alloys, CD4MCU, which is kind of a forerunner of beryllium-255. That alloy's been around since the 1930s. That alloy is a cast alloy. CD4MC was a cast designation. Castings are always annealed afterwards. So if you had to do any repair welding on it, you would use a more or less matching core material, and you would anneal it, and then it was okay. But in the as-welded condition, properties are off. 329, likewise, that was a rock material. Very popular in Japan, not so popular in the United States. But as a rock material, it has some very interesting properties. Again, in the as-welded condition, you would consider it unweldable because the mechanical properties and the corrosion properties are very poor. It's only after annealing that it develops these properties. Problem is that you get, in the as-welded condition, virtually 100% ferrite, and then the properties are those of a liquid stainless steel with very coarse grains. In other words, very poor toughness. Also, because there was a little bit of residual nitrogen in it, you got chromium nitride precipitates. So the corrosion resistance was also. You had to anneal at a temperature around 1100 degrees C or higher in order to get good welding toughness. And then what you were really doing was adjusting the balance of austenite versus ferrite. Second generation happened by accident, I believe. It happened in the late 70s and became popular in the 80s. The thing that triggered it was the development of the argon-oxygen decarburization system for refining stainless steels. In the argon-oxygen decarburization system, you blow argon with a small amount of oxygen in it into the liquid metal. The oxygen reacts with the carbon, takes the carbon out, and the argon is the carrier to help the bubbles get removed from the puddle, from the melt. But when you read the books about when AOD was developed, what you find out is that people right from the get-go with AOD were using air as a source of oxygen. And air is 80% nitrogen. So they accidentally got nitrogen into the metal. And voila, the weldability improved markedly. So that in the second generation of duplex stainless steels, the ones that proliferated in the 1980s, typified by 2304 and 2205, those materials had about 12 points of nitrogen in them. With 12 points of nitrogen in them, the heat affected zone was now somewhat sensitive to heat input. If you had high heat input, you would get good heat affected zone properties. If you had low heat input, you would not get good heat affected zone properties. It all depended on how much time at temperature the material had in order to produce a decent amount of austenite. And when this generation of base materials came about in the 1980s, it became very popular to adjust the thin metal composition to 9% nickel instead of 5%, so that you would get more austenite in the weld metal. That didn't do a thing for you for the heat effect. So you had to control the heat input in order to get a decent heat effect. Now, I want to point out one thing here. 2205 in the literature, it was always associated with UNS number S31803. And that's very important because it allowed for a rather low minimum nitrogen content, 0.08% minimum nitrogen, in order to satisfy UNS 31803. Now, two Japanese gentlemen, Professors Ogawa and Kotecki, back in the 1990s, did a remarkable study that was published in the Welding Metallurgy about alloy partitioning in duplex stainless steels. The trouble with the publication in the Welding Journal is that in those days, the Welding Journal did not publish in color in the research supplement. So that I don't think very many people appreciated the tremendous discovery that Ogawa and Kotecki had made. But they had a second publication of it that appeared in the IIW Commission 9. And I saw that. And it was one of those aha moments. I get it. So let me go through this in a little detail to point out what they discovered and how important it is for us. Okay. So what you have here is a rock 2205 type base material. In the upper left corner, you see the base material in the rock form, and you can see the layered appearance. The grayer material is ferrite, the white material is austenite. And then what they did was use an electron microprobe to look at the distribution of the alloying elements in that rock material. And each of the maps is color-coded so that you can see where the high concentration of an element is and where the low concentration is. So if you look to the ferrite area here, and you look to the chromium map that corresponds to it, you see the red color in the ferrite. And that corresponds to 25% chromium. The alloy only contains 22%. Conversely, if you look through the austenite area, which is blue here, that corresponds to 20% chromium. So there's a partitioning. Chromium promotes ferrite, so it segregates the ferrite under equilibrium conditions. Conversely, if you look at the nickel map, what you see over here in the ferrite area is low nickel. And now the blue color corresponds to 5% nickel. Okay. The alloy is nominally 6% nickel, so you got 5% nickel in the ferrite. And over in the austenite area, you have the red color, which corresponds to about 7 or 7.5% nickel. So the nickel has also partitioned. If you look at the molybdenum map looks just like the chromium map. The rich molybdenum area is the ferrite, the low molybdenum area is the austenite. And now we're saying the alloy is 3% molybdenum, but the ferrite contains almost 4% molybdenum, and the austenite contains 2.5%. So there's a partitioning of molybdenum. The most interesting alloy element, however, is the nitrogen. Now in the nitrogen color coding, blue corresponds to 0. Red corresponds to about 0.25, 0.3, something in that order. And if you look in the ferrite areas, it's 0. If you look in the austenite areas, it's around 0.2, 0.25 for an alloy that contains 0.12% nitrogen. So it's an almost complete partitioning of the nitrogen to the austenite and away from the ferrite. Now, if you take this same material and you make an autogenous weld, this is what you get. Autogenous gas tank. Same material. And this relates not only to the weld metal, but to the hottest part of the heat effect. And it's critical that I bring in the hottest part of the heat affected zone, although Ogawa and Kotecki showed this as weld metal, not as heat affected zone. But it applies to the heat affected zone as well. When you look at the microstructure in the upper left corner now, what you see is a big ferrite grain outlined by little plates of austenite on the grain boundary. And then in the center of the ferrite grain, there is all this black specks, the chromium nitrides, which I think Ellen showed this morning. And if you look very closely, you can see next to the austenite plates along the grain boundary, there's an area that's clean, doesn't have black specks, no chromium nitrides. Okay, now if we look at the partitioning of alloy elements, If you look at the chromium map, there's no partitioning evident. If you look at the nickel map, there's no partitioning evident. What you can see a little out of the nickel map is these little hexagonal areas that are slightly more yellow in the outline and green in the center. Okay? That tells you solidification core. It doesn't tell you anything about the transformation when ferrite transformed to austenite. This has to do with solidification core. If you look at the molybdenum map, again, you can see a little bit of the kind of coring or the yellow hexagonal shapes in there. But you don't see anything that suggests the microstructure up there. However, when you look at the nitrogen distribution, you can see the ferrite grain very clearly outlined by nitrogen, which is in the austenite plates on the grain box. You can see in the center of the grain an essentially nominal nitrogen content that's caused by a mixture of chromium nitrides and ferrite. And next to the grain boundary, you can see the zero blue color, zero nitrogen blue color, which means the nitrogen had a chance to get out of there. So nitrogen was diffusing towards the austenite out of the ferrite. Near the grain boundaries, the nitrogen can get out, but in the center of the grain, it can't. It doesn't have enough time. Now, you might say, well, what if I wanted to get rid of those nitrides? What would I do? I might take the nitrogen out, but then I'd have a ferritic stainless steel. Yeah, 100% ferrite. A better way to go, and this was referred to by Ellen again this morning, is put in more nitrogen. Instead of 12 points now, we have 18 points of nitrogen. Otherwise, it's the same composition, 2205. Now, when you look at the base metal microstructure, you can still see a big ferrite grain outlined by austenite plates, but there are all kinds of austenite plates crisscrossing the grain internally. Now, when you look at the alloy element mapping, you can see a little bit of the chromium partitioning. If you got really good imagination, I think you can see there's a tendency for a blue outline here. That's a ferrite grain boundary which is completely covered with austenite. This tells you that the transformation of the first formation of austenite took place at a higher temperature, where nickel, or where chromium had a chance to diffuse out of the austenite. And if you look at the nickel map, you still can't see anything but the little hexagonal shapes. Nickel is the slowest diffusing of all the elements. If you look at the molybdenum map, you can again see, in fact, you can see it better now, that blue outline of the big ferrite grain, where the molybdenum is bailing out of the areas that transform to austenite. And if you look to the nitrogen map, you can see the same big ferrite grain outlined by high nitrogen on the grain boundary. You've got all of these austenite plates inside the grain, which are also full of nitrogen. And then you've got ferrite areas that are completely clear of nitrogen. Now you've got good properties. It's the nitrogen that makes the alloy welding. Because that promotes formation of austenite at high temperatures, the diffusion can go on. So, one of the things we like to do now is, as a result of this, we try adding nitrogen to the shielding gas to keep it in the weld metal. We increase the nickel content in the filler metal to 9% to help the weld metal. And with this addition of nickel, we now call the filler metal 2209 instead of 2205 to tell you that it's 9% nickel instead of 5% nickel. But this brings us to the third generation of duplex stainless steels. And 2205 appears in this generation as well. But now it has a new UNS number. Instead of 31803, you see 32205. The ASME code in year 2000 redefined the 2205 base material by this UNS number 32205. The minimum nitrogen content in that alloy is now 14 points instead of 8. And that has a big effect on the weldability. Now, the heat affected zone is not very sensitive to heating. You can go from a ½ kilojoule per millimeter to 2.5 kilojoules per millimeter and still get good heat affected zone cracking. A big advance. Partly for historical reasons, but partly also to improve the toughness of the weld metal. The filler metals still tend to be high in nickel. And now we start looking at pitting resistance, but it's only after we got to the third generation of duplex stainless steels that we thought at all about pitting resistance. As I said earlier, there was chloride stress corrosion cracking that was the main reason for duplex. And now we can look at this pitting resistance index, which includes nitrogen. And I'll give you a slightly different version of the pitting resistance index because there's a factor for tungsten in it. I think when you saw the one this morning, you saw it without tungsten. Tungsten is considered to be half as effective as molybdenum in terms of providing resistance to pitting. Otherwise, for a tungsten-free alloy, the pitting resistance index calculated this way is the same as the way you saw it this morning. But for 0 and 100, which contains deliberate additions of tungsten, this matters. So the third generation of duplexes have rather modest pitting resistance. They've got pitting resistance index numbers in the low to mid-30s. What you would like is to get up to 40 because then you can be competitive with the so-called superaustenitics. These are the alloys of 20 chrome, 25 nickel, like 254 SMO or AL6XF. And that brought us to the fourth generation of duplex stainless steels. And these are the so-called superferritics. And there are two main alloys in the rod form, 2507 and 0 and 100. And here you can see 0 and 100 contains an addition of tungsten, which gets its pitting resistance index up over 40. And then the cast version, CD3MM, is the cast version 2507. And CD3MWCUM, that's a mouthful, I really say that. Anyway, those are the cast equivalents for 2507 and 0 and 100 respectively. So that's your fourth generation of ferritic stainless or duplex stainless steels. Mechanical properties of the super duplex stainless steels are really outstanding. This is like HY80 steel with corrosion resistance. You're looking at 80 KSI minimum yield strength in the super duplex. You will notice that the yield strength numbers for the cast materials are lower. And that's caused by the fact that when you anneal the material, the microstructure tends to spiritize. And part of the strength in a duplex stainless steel comes from the layered structure of ferrite and austenitic. When you lose that layered structure, you lose some strength. So you have to be used to that motion. Where do we apply these things? I was going through a bit this morning. There's a lot of environments, including with the super duplexes, seawater. They're resistant to seawater, and that's quite impressive. People make things out of 316 stainless and they put them in seawater and you don't understand why it corrodes, because gosh, it's stainless. And it's not stainless in seawater. Okay, so that's just kind of a list of things that you'll find. One of the interesting applications for the super duplexes is the flue gas desulfurizers. Flue gas desulfurizers have high temperature areas and low temperature areas. You don't use super duplex in the high temperature part of the flue gas desulfurizer. What you We use it in the low temperature. And it's quite resistant to the acids and the chlorides and whatnot that exist in that pipe. Seems a little odd to think about the way this happened, but after the fourth generation became popular, there was a kind of a relook at the low alloy duplex stainless steels that are so-called lean duplexes. Now, originally I had put 2304 in the second generation duplexes, but I think today we would reassign it to the lean duplexes, which really came after the fourth generation. But the 2101 alloy is probably the most prolific today of the lean duplexes. This alloy is very low in nickel, only 1.5% nickel, but it's got 5% manganese in it. Now the function of the manganese is not to promote austenite. You have to get that notion out of your head. Manganese does not promote austenite. Those of you who know the Sheffer diagram and see manganese in there as an austenitizer, get that out of your head. It doesn't do it. But what manganese does do is two things. One is, if you get austenite, it enhances the stability of the austenite with respect to transformation to martensite at low temperature. So that 5% manganese prevents formation of martensite at low temperature. But the other thing that it does is it enhances the solubility of the metal for nitrogen. And it's nitrogen that really makes the austenite form in the first place. But anyway, the idea of this alloy and the other lean duplex, the 2304 and the 2404, I think was mentioned in some of you. The idea with those is to get corrosion resistance that's more or less competitive with 304L, but do it with very little nickel. Here you're talking about 1.5% nickel instead of roughly 9% nickel in the 304L. Now, an interesting thing about these things, I told you with third generation duplexes that they were not sensitive to heating with normal arc welding processes. I should have added. I didn't deliver it. The third generation of duplexes can be welded by the arc processes. They cannot be welded by resistance welding. They cannot be welded by laser beam welding because the metal cools too fast, even with high nitrogen. However, 2101 is different. I'm indebted to Alan Weston for these four micrograms. We actually did some work on resistance welding of 2101. And you have to do some tricks with 2101 if you're going to resistance welding. The idea here again is to get some transformation to austenite. In the as-welded condition in a normal resistance weld, you get a little austenite on the grain boundaries and a little austenite inside and a lot of chromium nitrides. But in a resistance welding machine, after the resistance welding cycle itself is done, you've made a resistance weld, you can pulse the resistance welder a second time. A 2-second pulse of energy, 2 seconds, drops the ferrite content from 83% to 74%. And what it particularly does, I'm not sure that you can see it as well here as you might see it in a paper version, but the amount of the chromium nitrides in the dark areas here is greatly reduced. They're discontinuous. You can live with it. You can get useful mechanical properties out of a resistance weld that is post-weld heated with this little 2-second post-weld heat treatment. You can get useful mechanical properties and useful corrosion resistance. So you can make things like dimple jacket heat exchangers by resistance welding. metals for these things are classified both by AWS and in the ISO standards. And so what you see in AWS is 2209, which is directed at 2205 type base material. The 2307 is intended for the lean duplexes. The alloy was originally developed for 2101, but it also works for 2304. That alloy is quite different in composition. It has quite a bit of nickel compared to the 2101 base material. The reason for that is in the as-welded condition, if you have a 2101 composition and you pick up oxygen from a flux shielded process, you get lousy mechanical properties, in particular very poor toughness and even very poor tensile ductility. But by depending on nickel to help you out, you get better properties. So the 2307 composition or the 2307NL as the European or ISO standard terms it, is adequate for lean duplex. 2553 exists only in AWS. It doesn't exist in the European or ISO standard. But this is essentially a matching filler material for the beryllium 255, which shows up back in the. This is the beryllium 255 or alloy 255. This is the rock composition. Now we go to the filler metal. The 2553 matches that composition exactly. And you would use it primarily on cast material, not on rock material, because with that low nickel, it's going to have rather poor properties. And when it's annealed, then it has good properties. The 2593, which is the next one down, that is the filler metal that would be recommended for the as-welded condition on beryllium. So you actually have two filler metals, one for the for the as-weld, for the castings, and one for the as-welded. And then 2594 is the filler material intended for 2507 duplex, super duplex. And the last one, 2595, is for the 0100. Now, in most practical applications of super duplex, people use 2594 and 2595 interchangeably for 0100 and 2507, and I don't think anyone has ever shown any convincing evidence that one or the other is better. Now, we talked about hyperduplex. That was mentioned again this morning. There are two hyperduplex alloys that have seen some appearance in the literature. 2707, which is a 27% chromium, 7 nickel, 5 moly, and 0.4 nitrogen material. Has a PREM that doesn't quite make 50, but I think that's a little accident that came out with it. And then there's a second one, this 3207, which is 32 chrome, 7 nickel, but it's not so high moly. And that actually does have a PREM above 50. The filler material that is proposed for these things by Sandvik, who is the purveyor of the material, is 27 chrome, 9 nickel, 5 moly, 0.4 nitrogen, and it's the same filler material for both cases. That filler material is only available as gas tungsten arc filler material. That's the only welding method that's ever been used on those things, as far as I know, to any extent. And at the moment, I don't know that there is any commercially significant application of them.
Urea
They use
They are
it?
using that, yes.
Urea? I thought urea manufacture was very aggressive towards ferrite.
That's the only one they can use.
Okay.
In certain areas, and not all, certain areas.
All right. Thanks for that. But anyway, this is sort of like, maybe that's what's in the future, maybe not. If it's not a commercial success soon, I think it will happen. Okay, now because of the ferrite phase in the duplexes, there is a lot of possibility for precipitation. These were mentioned also this morning. The alpha prime phase, which forms a temperature range of about 400 to 540 C. The sigma phase, which forms between 500 and 1070 C. And the chi phase, which can go up to 1100 C1. So that essentially prohibits you from using the alloy anywhere from below 400 to 1100. Well, that alloy doesn't have any useful properties above 1100 degrees C. It's sort of like peanut butter in terms of mechanical properties. So the real interest is in below 400 C. Now here you will see this is the temperature range where it forms, where the alpha prime phase will form in a few hundred hours. If you go to 10,000 hours, that temperature comes down. And so people will say 300 degrees C is the maximum surface temperature for these alloys, or maybe even 250. So those are all limitations. Now the alpha prime embrittlement occurs when, not in the metallic compound, but when ferrite partitions into two ferrites, an iron-rich ferrite and a chromium-rich ferrite. And if you look at the binary iron-chromium phase diagram, what you will see is that two-phase decomposition of ferrite into an iron-rich ferrite and a chromium-rich ferrite, when that occurs, the chromium-rich ferrite contains over 90% chromium. And that horribly depletes the chromium content in the matrix. And so the matrix becomes very susceptible to corrosion. A guy named Tavares published a paper on the internet from which I borrowed this material. What he's looking at here is thin wall pipe, so it's not the sharpened impact value shouldn't alarm you too much. But what he's looking at here is the mechanical properties of 2205 material using the old 31803 number, so I'm not sure exactly what the nitrogen number is. But he's looking at time at 475 degrees C on the horizontal axis. And then on the vertical axis, on one side we're looking at impact energy in joules. And these are very subsized Sharpie specimens because of the fact that it was thin wall material. So what you see in the impact results, Sharpies start out at a bit over 30 joules and they drop in something on the order of 100 hours to less than half. And if you also look at the hardness of the material, he's using Burdell hardness. So the hardness starts at a number in the 220 area and it goes up with increasing time and temperature, so that you're up in the area of 350 Burdell after 500 hours. So there's a serious hardening of the alloy and a serious embrittlement of the alloy. And if you look at corrosion, what it was done here was to use a electrochemical pitting cell to just increase the potential until you got the first surge of current in the electrochemical cell. And that's the initiation of pitting. Then you stop the process immediately. So instead of getting big pits that you can stick your finger into or stick a ballpoint pen into or something like that, you get little bitty pits. And you can see here, all the pits are in the dark etching material, which is the ferrite. There are no pits whatsoever in the austen. You can't see the alpha prime. You need a scanning transmission electron microscope to see that. But you can see the pits that result from the chromium depletion next to the alpha prime condition. So that's very destructive to the properties of the material. Heat treatment of duplex stainless steels, especially when they've been welded, is a little bit of tricky business. Because we're saying, well, you can go, you've got a whole temperature range from 400 degrees Celsius up to something over 1050, 1070 degrees C, where bad phase is formed. Sigma phase, pi phase, and alpha prime. The ASTM standard A240 used to call for annealing of 2205 at a minimum temperature of 1040 degrees. And that was just fine for the basic material. It was just fine for matching composition weld method. But it turns out it wasn't just fine for the 9% nickel filler material. This was illustrated by a company that gave a paper at one of the Duplex World Conferences back in the Netherlands in the 1990s, in which they reported on fabrication of a very large dish head for a 2205 vessel. The head was large enough that it could not be fabricated out of one plate of 2205 material. So they welded a number of plates together using 9% nickel filler material. And then they cold formed it to make this dish head. And after they cold formed it, they saw some damage to the mechanical properties in terms of loss of toughness because of the plastic film. So they went to annealing. The annealing said 1040 degrees C minimum. So they went up to 1050 or 1060, I don't remember the exact number. Water quenched. Well, the head warped slightly during the annealing, so they needed to true it up a little bit. So they put it back in the forming press, and they were just going to give it a little bit of nudge to true it up, and it fractured. The welds unzipped. They literally unzipped, and the plates came apart. They investigated and found that the weld metal was loaded with sigma phase. Interestingly enough, I gave another paper at the same conference in which I talked about heat treatment of duplex stainless steels. And to begin with, on that paper, I referred back to an old diagram that was developed by a gentleman named Paul Grobner that worked for Climax Molybdenum Company back in the 1970s and 80s. His diagram, which he shows here, which I show here, is looking at the phases that are stable as a function of temperature in a 25% chromium, 3.5% molybdenum alloy with varying amounts of nickel. So what you have on the horizontal axis here is nickel content increasing from 0 to 30%. And all of these alloys contain the same amount of chromium and molybdenum. So what you have here now are temperature fields for 100% ferrite, ferrite plus austenite, austenite, ferrite plus sigma, ferrite plus austenite plus sigma, and austenite plus sigma. The important feature of this diagram is the sigma solidus boundary. That's the boundary above which sigma vanishes. And here you can see that as the nickel content increases, the temperature of the sigma solidus rises. So when we went from a 5% nickel base material to a 9% nickel filler metal, we raised the sigma solidus temperature by about 100 degrees Celsius. Grobner's diagram was there, but nobody saw it. Well, I was fooling around with duplex stainless filler metals at the same time, and I got to looking into heat heat treating of these things because I was making some filler metals for a purveyor of duplex casting. So I made a weld metal of a 2209 composition. I annealed it at 1065 degrees, which is 25 degrees higher than the ASTM recommended minimum. So I should have been safe. And I water quenched it. And I had Sharpie specimens, tensile specimens, machined from it, and a mellographic specimen. Well, the first specimen that got addressed in my laboratory was Sharpie specimen, impact specimen. So I have a technician in the, we called it affectionately the busing lab. That was the lab where we broke things, like tensile specimens and impact specimens. And I asked him to break specimens at room temperature to start out. So he got this sample. He broke the first couple impact specimens at room temperature, and then he came running down the hall to my office. He goes, Doc, you got to see this. You got to see this. What? So I go down to the busting lab, and he says, now watch this. And he puts the specimen in the impact specimen in the impact machine at room temperature. Hits the hammer. Now, when you got a good impact specimen, it's going to go thud. This one went blink. 3 joules. Full-size impact, not a subscale. 3 joules. Then, we measured the tensile elongation, and it was about 10 or 12%. Then I looked at the microstructure, and here was the answer. All these white islands that are outlined but not touched, sigma phase. Pretty big hunks of sigma phase. Dark stuff, of course, that's the ferrite. And the white stuff is the oxide. In the as welded condition, I measured the ferrite content of that weld. And it was 45 ferrite number. I use a magnetic method to measure the ferrite, not another part. 45 ferrite number. In this condition, it was 22 ferrite. In other words, half of the ferrite was 6 grams. So I said, well, maybe we just didn't anneal it long enough. So instead of 2 hours at 1065, I went to 72 hours at 1065. And I got exactly the same thing. It wasn't that I hadn't heated long enough to dissolve the sigma phase. It was that the sigma phase was stable at 1065. Then I took it up to 1100 degrees C. 1110. But anyway, after that anneal, I got good impacts, I got good ductility, and I measured the ferrite number again. And you know what? It was 45 again. The reaction was it was completely reversible. I could get the sigma to go back into solution, and I got ferrite. Now that was kind of interesting to me because when you start out with high ferrite welding, let's say you get a 60 or 70 ferrite number in the as welded condition and you anneal it, you will see the ferrite number drops. Drops appreciably. But if you start out with a ferrite number around 45, it doesn't drop. And the reason is because the alloy started to form austenite at higher temperature, and you got very close to equilibrium partitioning, very close to equilibrium amount of austenite. So when you say, is the ferrite stable? The question really is, how much ferrite's there. If you got a lot of ferrite, no, it's not all stable. If you only got a little bit of ferrite there, yeah, it's stable. Okay, so as a result of that, ASTM revised ASTM A480 to change the annealing temperatures for the 9205 and similar duplexes. Now, it was mentioned this morning that you never want to make an autogenous weld in a duplex stainless because you will have horrible mechanical problems. When you make the root pass in a pipe, you generally do that by gas tungsten alcohol. And welders don't like open roots. As a matter of fact, they hate it. And they hate you for telling them you have to make a weld in an open root. But the conventional wisdom is you got to use open roots. And here we're talking about a root gap that might be 2 to 3 millimeters. Some people say 3 to 4 millimeters, depending upon which welding process you're using. Now this STT, that's a surface tension transfer. That's a Lincoln trade name for gas metal arc short circuit transfer with a controlled waveform. And there are other people who make similar material. They all come to the 3 to 4 millimeter recommendation for root gap. But anybody in this room a welder? I'm going to insult welders.
A very big one here.
Yeah, at least 3 welders. Okay. I'm going to be careful. All right. I'm going to tell you 2 things. Nobody believes filler metal producers because everybody knows filler metal producers lie. So they always check on us. I'm a filler metal producer. I've been checked countless times. They don't believe us when we tell us how much ferrite's in something. They don't believe us when we tell them how much tensile strength they're going to get or how much they check on us. Well, you shouldn't believe welders either. They cheat. And when you tell them that they got to have a 2 to 3 or a 3 to 4 millimeter root gap, you're not looking. They might squeeze it down to make their job easier. It's much easier to bridge a closed root than an open. Am I telling the truth so far, you guys?
Oh, kinda.
Okay, so what are you going to do about this as an engineer? Are you going to let the welders cheat when you next to them? The way a lot of fabrication is done, particularly around the North Sea, where there's a lot of duplex and walls, is to put a little dent on either side of the joint preparation on the surface. And the dent is put there a fixed distance away from the edge of the joint preparation so that it won't be melted by the welder. It'll still be there afterwards. That's called a witness mark. Then you measure the distance between those 2 dents after the welding is done, and you can catch the welder cheating.
Except that if you weld a duplex, you're going to shrink it 3, 4 millimeters, sometimes even more.
That's all figured in, though. That's all figured in. Those things are called witness marks. I don't know if they're still popular in the North Sea area. Fred Beastie probably knows more about that than I do, but I know they were very popular at one time. They're still using them, Fred?
Yes.
Okay. All right, so I had to tell you about filler metal producers lying before I told you about welders cheating. So we would at least share the blame, all right? Okay, now, high nitrogen works well for control of ferrite in the heat effective zone, but nitrogen tends to be lost from the weld pool. I think Ellen referred to that this morning. So it's common to add some nitrogen to the shielding gas, particularly in gas tungsten arc welding, which has the greatest tendency to lose nitrogen. And I will confess to you right now that if you use even 2% nitrogen in the shielding gas in gas tungsten arc welding, your tungsten is going to deteriorate more rapidly than it would without the nitrogen addition. So that I can say, tough, deal with. Because that's the only way you're going to get good properties in the super duplex stainless. You got to get the nitrogen in there. In the filler metals, we still use the 9% nickel, as I mentioned. But this is the kind of microstructure you can expect if you add nitrogen to the shielding gas in a super duplex weld method. This is the 2594 and 25% base material. Here you can see the heat affected zone has a little more ferrite in it than the base material. Has a little more ferrite. But it's enough austenite there to prevent any extensive nitride precipitation. I'll go back to Julian's talk this morning. You will never see zero intermetallics or zero nitrides. I agree with you completely. There's going to be some there. The question is, are we going to do any damage? That's the kind of microstructure you should have. This is looking at gas tungsten arc welding with pure argon versus 5% nitrogen. And with pure argon, you'll still get pretty good impacts, but you've got these pretty large ferrite areas which are at risk for getting nitride precipitation. Whereas when you add the nitrogen to the shielding gas, you have very little in the way of large ferrite areas, and therefore much less tendency to get all the nitrides. Now, another thing that was referred to this morning, but I want to mention it again, perhaps to reinforce it. The worst pipe weld for duplex stainless steel is a guy who learned to weld pipe on carbon steel. And the reason is because when he learned to weld pipe on carbon steel, he learned cold, fast root pass followed by hot pass. And that's a long thing to do with duplex, and especially with super. This is a heat affected zone, actually, from a, I'm sorry, this is welding. This is welding. Root pass came from a customer complaint that is failing toughness in the root area. Put in a thin root pass, followed by a hot pass. And the end result was that the root pass solidified fast enough that some nitrogen was held in solution in the ferrite. Maybe it was even some cold nitrogen, we don't know. But the hot pass reheated it and caused secondary austenite to precipitate and sigma. It's pretty hard to tell which is the secondary austenite and which is the sigma phase in the center of those high ferrite areas. But that's a mixture of secondary austenite and sigma phase. So the right way to do things is to have the heat input of the root pass be at least as high as the heat input for the second pass. You have to protect the root pass because after all, in a pipe, that's what's going to be exposed to the corrosion. And I will also tell you that if you have some intermetallics and some chromium nitrides in the interior of the material, where it's not exposed to the corrosion, if it doesn't hurt your impacts, it doesn't hurt anything. Let it be.
But if it's at the surface, is a different story.
At the surface is a very different story, and it's the root pass that's at the surface. Now, one other thing that hasn't been mentioned yet is diffusible hydrogen in duplex stainless steel. It's stainless. You don't have to worry about diffusible hydrogen. The hell you don't. You have to worry about hydrogen in duplex stainless steel, especially when the ferrite content gets high. You know, the specifications will tell you, oh, you can use 30 to 70% ferrite. If you got 70% ferrite and you got appreciable diffusible hydrogen, you're going to have a problem. There was a 2205 pipeline, Fred, you probably remember this one, in Malaysia, back in the early 80s, I think it was. 2205, welded with covered electrodes. And it was welded above ground on stands because the area where it was being laid was swampy. So they didn't put it into the trench until after all the welds were made. And when they went to lift the pipe off the stands with a whole series of cranes and lay it into the ditch, they very slightly deformed it because not all the cranes lifted at the same rate, and welds broke. They got to looking at it, it was hydrogen damage. It was a high ferrite weld, I admit to that, it was a very high ferrite weld. But it was also a weld made with covered electrodes that had been exposed to the very dry environment you have in the Malaysian Peninsula. They got kind of stuck, and they produced hydrogen cracks. And oddly enough, I managed to do that in the lab with a flux core wire before I realized what was going on. I was looking at high ferrite weld. So this was a 2553 type weld metal. It had a ferrite number of about 80, if I remember correctly. And what you could see on this is the fracture end of a tensile specimen, a half-inch diameter tensile specimen. Right here you have a very large fisheye. You guys work with low alloy steels, you know what I mean by fisheyes. They're crystalline fractures caused by infusible hydrogen. The tensile elongation of that stuff is only about 10 or 12%. Whereas duplex stainless steel should be treated as, when you're welding it, as if it were something requiring low hydrogen cracking. That means you keep your filler metals dry, especially flux shielded filler metals, and that includes submerged dry flux. You're going to keep it dry. No different from welding low alloy high strength steel. Keep it dry. Now, if you buy filler metal that's at the low end of the ferrite range, in the 30 to 40 range, you're pretty much immune to this. But the problem is the specifications are saying 30 to 70% ferrite. When you get up to the high end of that range, you're susceptible to this. One thing I want to tell you never want to do is use gas tungsten arc and put hydrogen in the shielding gas. It's okay to put it in the root gas when it doesn't get into the arc. Don't put it in the shielding gas because hydrogen will get into the weld metal. And then if you have a high ferrite weld metal, you're susceptible to exactly that. Okay, so we get to the, I just want to re-emphasize one more thing, and that is if you remelt duplex stainless steel by gas tungsten arc welding, you're going to get high ferrite. If you try to dress the surface with gas tungsten arc without ferrite metal, you're asking for trouble. You don't want to do that. I think Ellen said that this morning, and I completely agree with her there. So the rules of the game to weld duplex stainless: high nickel filler material, avoid high dilution welding, or if you are going to do high dilution welding, you're going to want to anneal afterwards. You know, the longitudinal seam in pipe is oftentimes welded by a plasma arc keyhole with no filler metal or very little filler metal, or by submerged arc with very high dilution process. And as long as you anneal the pipe afterwards, that's just fine. You also have to avoid the entire temperature range from 300 to about 1100 degrees Celsius. Or you got to heat treat at 1120 to be sure you're going to dissolve all the undesirable phases. And water quench. You got to water quench more or less directly from 1120, or at least above 1040. Now, the purveyors of the beryllium-255 base material have insisted for a long time that annealing had to be done at 1040 degrees. That you shouldn't anneal at a higher temperature because you'll still have some residual nitrogen in the ferrite, and that might cause chlorine nitrates. And so one of the things I worked out in my years at McKay was what we call a step anneal, where the initial annealing temperature was 1120, and then we drop the temperature in the furnace to 1040. Held it at 1040 for only a few minutes, and then yanked it out and let it quench. And then we could get good annealed properties in the Alloy 255 weld metal. And we could follow their recommendations. So that step anneal I know is being used other places. I've seen it referred to in the estimates before. So with that, I'll conclude by saying, as was said this morning, welding of duplex stainless is different. But not different. Follow the rules, everything will be good. Now, I would disagree with one thing that was said this morning about distortion. I think, Julia, you said it? Okay. And I think maybe Ellen said it too, that you get less distortion with duplex. Well, that depends. One of the things you have to appreciate is that duplex is a whole lot stronger than austenitic. If you allow it to free move, austenitic stainless will move more than duplex. But if you do a half-assed job of restraint, duplex will move more than austenitic. If you're going to restrain duplex when you weld it, you don't want to use bungee cords to hold it down. You want to use massive restraint to keep it from distorting. Because it develops strength more rapidly and it is stronger than austenitics. It will pull more if you do a light restraint job. You've got to do heavy restraint. So with that, I'll close and open the floor for any questions you might have. I think I said that in a few minutes.
Okay.